Hi folks, I want to introduce you to 2D linear systems. So far we've been studying 1D systems where we only have one dependent variable x. And we haven't been particularly focused on linear versus nonlinear. We've been studying systems that look like x dot equals f of x for any old f of x. But now we're going to introduce another dependent variable. We're going to call it y. So we'll have two dependent variables, x and y. And in order to be able to make some progress on this system, obviously there's more going on if we have two dependent variables. In order to make progress, we're going to restrict ourselves to special class of systems like this, and these are going to be linear systems. And generically speaking, a 2D linear system has a form written right here. It's going to look like x dot equals some linear combination of x and y dot equals some other linear combination of x and y. So again, the dependent variables here are x and y, and our parameters, or some numbers, whatever the constants that go into the equation, are going to be a, b, c, and d. Okay, great. Now, you have some knowledge of linear algebra. You probably remember some linear algebra, but we're gonna review it as we go along. But an important thing to point out here is that this is a linear system, and that means that I can talk about it in terms of linear algebra, and it's natural to do so, and we're gonna talk about it that way. And so it's good to look at it in terms of linear algebra. So this system of equations right here, these two equations, can be written in matrix form by just consolidating. So x and y are going to go into a single vector, and I'll just put the dots over the top of them in this vector. And that's going to be equal to the matrix product with the vector x and y. And so this is just an equivalent way of writing what's up here. If I just multiply these matrices and look at the equality of the two components, I've written that thing in matrix form. Now, even more linear algebra-like, I can call this matrix A. So I'll write the matrix A equals A, B, C, D. And I'm going to put these two dependent variables in a vector, x, y. And I'm going to write this whole thing, this, and this, all equivalently as x dot equals AX. And so that's the vector x, put a dot over the top of it, that's equal to the matrix times the vector x. So all these three things are the different ways of writing the same thing. But this one kind of looks the most like the linear algebra that you're used to, hopefully, and is going to be a viewpoint that we would like to have when we're going to use linear algebra to try to solve problems related to this 2D linear system. Okay, I'd like to start with an example of a 2D linear system. And this one is going to be pretty simple, but it's going to exhibit a lot of behaviors and get some cool pictures out of it, even though it's a pretty simple system. Good place to start. Okay, so the example is x dot equals ax and y dot equals minus y. I'm going to think of a like a parameter, and the punchline, we're gonna think about different values of a, and so we're going to let a vary and kind of see the different behaviors we can get out of this linear system. But for now, let's just look at this guy. It's x dot equals ax, y dot equals minus y. And as a reminder, the matrix form, I can write it in matrix form. And what is that matrix going to be? It's going to be a, 0, and 0, minus 1. So x dot equals this matrix times x. That's that system in matrix form. Now, one thing to notice, and this is a little vocabulary word, one thing to notice is that this system is decoupled. It's not coupled, it's decoupled. And what that means is that essentially there's no y appearing in the differential equation for x, and there's no x appearing in the differential equation for y. So essentially these two guys are just living separate lives, doing their own thing. They can behave together, but there's no interaction between the two. The value of y doesn't influence x and vice versa. Okay. And because it's decoupled, we just basically have two separate 1D systems, and we can solve them. Okay, so not that amazing yet, but let's solve it, and let's just kind of see what kind of pictures we can draw. So x of t, we'll solve it. This is an exponential decay or growth depending on the value of a. That's x of t equals x naught e to the at, where x naught is the initial value. That's when you plug in t equals 0. And y of t equals y naught e to the minus t. And again, y naught is the initial value of y. So let's think about varying a and drawing some pictures to see the different kinds of pictures we can get in 2D, and then we'll look at systems that are coupled and maybe are harder to analyze. Okay, first example, we'll take a equals minus 1. So our generic example becomes x dot equals minus x and y dot equals minus y. Great, two decoupled exponential decay equations. The solutions, as we've seen before, are x naught e to the minus t or y naught e to the minus t. So this describes essentially exponential decay, totally separate. How are we going to picture this, or what does this have to do with 2D systems? Well, I introduce you to the phase plane. The phase plane is like the phase line, except, well, it's a plane. So we're going to have two axes, an x-axis and a y-axis. And instead of drawing just the equilibria and some arrows indicating which direction you're going to move toward the equilibrium, we now have paths in this plane. We have curves or lines or some kind of graphs of the solutions. Not exactly graphs, they're more the images of them. But pictures of the solutions, and they can move around in the plane. In this case, these solutions are going to start somewhere. Let's say one solution starts right here. This is the point x naught, y naught. And what is it going to do? It's going to exponentially decay toward the origin. And it's going to do so along a line. The reason it does so along a line is because the decay is essentially the same in both coordinates, e to the minus t and e to the minus t. So you start somewhere in the plane. I'm going to start with an initial value, x naught, y naught. And then I let my solution run. It's going to decay exponentially toward the origin. And that's how I picture, that's how I graph kind of like all of the possible solutions at one time. This is what takes the place of the phase line for two-dimensional systems. Great, so it's the phase plane. And again, the moral of the story here is that for this particular example with a equals minus 1, I will see exponential decay toward the origin for all possible initial values. Now, I've got one more piece of little vocabulary here, and that is that I've got an equilibrium, a stable equilibrium at the origin. If I plug in 0, 0, I don't go anywhere. I just end up at 0, 0 for all time. And all these solutions, no matter where I start, they all decay toward that equilibrium. And that equilibrium is called a stable node. Okay, so it's kind of the analog of a stable fixed point in 1D. But there'll be different kinds of stability, as we'll see. Okay, another example. Let's take a equals minus 2. Then our system becomes x dot equals minus 2x and y dot equals minus y. Again, totally decoupled. We could solve this, and we've got two kind of separate equations that are one-dimensional equations. But again, we can combine them, and we can start to get some intuition as to how we're going to think about 2D systems. So this time, before you look at anything down here, let's think about what, just generally, qualitatively, what these solutions are doing. X is decaying more quickly. Y is decaying more slowly. So X is going to get closer to 0 more quickly. So if I start out here, let's say I start right here, I'm not going to go in along a straight line like before. Instead, what I'm going to do is X is going to shrink down more quickly, while Y shrinks. So I'm going to come in along a curved line, which squashes X more quickly in time and squashes Y more slowly. And it may not be clear what these curves are, exactly what their shape is, but we can actually look at the equation itself. We have the solutions, so we can do a lot of things with these solutions. We can look at these solutions and we can say, all right, if I take x over y squared, that ratio is x naught e to the minus 2t over y naught squared e to the minus 2t. And that gives me a constant ratio for a given solution if I'm on a fixed solution curve. I have x naught over y naught squared. So that says that the solutions actually trace out the paths of parabolas. You may not always be able to do something so explicit, but in this case we have the solutions, so we might as well. And so these solutions decay along parabolas. And these parabolas are given essentially by x equals x naught over y squared times y squared. So the relationship of this path that you see here, the relationship between the x and the y coordinate is one that's given by a parabolic relationship. Okay, great. So let's think about this a little bit more. There's a few more kind of interesting things happening in this picture. One, let's say we start on the x-axis. That means that y starts at 0. Well, that means that y should stay at 0. So if I start on this x-axis, I'm just going to decay right toward the origin, okay, along the x-axis. Same thing goes for the y-axis. If x starts at 0, I'll decay right along the y-axis towards 0. Anywhere else, really, and I'm going to start decaying along a parabolic path. The other thing to notice here is that if I start at the origin, I stay there. That's an equilibrium for both of these guys just stay at 0. Okay, great. So that's another example where I can get a different, even a more interesting picture by varying A. Let's keep doing this. Okay, now time for one of my favorite examples. We're going to take A equals 1. Now something substantial has changed. We're going to have x dot equals x and y dot equals minus y. This time, y continues to be this exponential decay, but now x is exponential growth, and something cool is going to happen. So let's just think about this again piece by piece. We're going to put the skeleton together over here of this phase plane. So let's think about what's happening along the x and the y axes before we worry about the other stuff in this picture. So for example, if I start on the x-axis, anywhere along on this x-axis, then y starts out at 0. What am I going to do? Well, I'm going to grow exponentially. So if I start out on the positive side of the x-axis, I'll grow exponentially this way. Start out on the negative side, I'll grow exponentially this way. That's what happens along the x-axis. So I've got these kind of straight line solutions. On the other hand, what happens along the y-axis? Well, if I start on the y-axis, I'm going to decay exponentially toward the origin. So if I start out up here, I'll decay. Start out down here, I'll decay. Well, what happens in between is kind of just like compatibility somehow. So if I start out up here, well, then y is going to be dominating. I'm going to be shrinking down. But meanwhile, my x is growing, and eventually y is getting very close to 0, but my x is growing exponentially, so I sort of zing off this way. Same deal over here. Start way up here. Let's say, big Y, small x. X is growing exponentially, y is shrinking exponentially, and eventually x is going to grow, y is close to 0, x is getting bigger and bigger, so I'm going to zoom off this way. Same kind of reasoning for these other parts. So this is a new kind of equilibrium. It's totally different. Sometimes the solutions tend toward it. Most of the time they tend away from it. But over here, they sort of tend toward it a little bit, but then zing away. This is called a saddle. Okay, it's called a saddle. Okay, and if we do a little bit of analysis, since we have these solutions explicitly, we can combine them algebraically to see what shape these curves are. And what we'll discover is that they're hyperbolas. And if we take the product, x times y, we see that the e to the t and the e to the minus t cancel out. And so we see that that's a constant, depending on which solution path we're on. So x times y is x naught times y naught. And so we have x times y equals a constant. That's what these shapes are here, these curves, which are hyperbolas. Great.